On July 30th, 1976, two robots landed on Mars and ran an experiment that returned a result no one expected, and almost everyone dismissed. The Viking 1 lander touched down in Kryze Planitia, a vast Martian plane carrying instruments designed to answer one question: is there life on Mars? But the answer that came back wasn't a clean yes or no. It was a whisper, ambiguous, unsettling, and almost immediately buried under scientific skepticism that still holds today. To understand why this moment mattered, you need to know what Viking was actually looking for. The landers carried 4 biological instruments, each one a miniature laboratory. The most famous, the labeled release experiment, worked like this. Soil samples were mixed with nutrients containing radioactive carbon-14. If microbes ate those nutrients, they'd exhale radioactive gas. Viking would detect it. Simple, elegant, and as it turned out, deeply controversial. On Sol 8, that's day 8 of the mission, Viking's sensors detected a spike in radioactive gas. The instruments registered a positive result. Gas was being produced. Something or someone appeared to be metabolizing the nutrients. The science team's heart rates probably climbed. This was the moment, the signal, life. But then something odd happened. The gas production stopped. Subsequent tests showed no repeating pattern, no second spike, no confirmation. The scientific consensus shifted almost instantly. It was a false positive, a chemical reaction, not biological, a mirage of meaning in dead dust. Yet here's what kept some researchers awake. The other 3 biological experiments returned negative results. But the labeled release didn't just return negative, it returned anomalous. Why would a purely chemical reaction produce that specific spike, then nothing? Why no follow-up signal? In 1997, more than 2 decades later, a biochemist named Dr. Gilbert Levin, who designed the labeled release experiment, published a controversial reanalysis. He argued that the pattern of gas production matched what Martian microbes might do, not what chemistry alone would do. The scientific community largely ignored him, but the data was still there, still unexplained. The real problem wasn't the data, it was context. In 1976, Mars was thought to be even more hostile than we know it today, a planet scoured by radiation, devoid of liquid water, chemically sterile. The idea of life there seemed absurd. So when the results came back ambiguous, the scientific prior, the assumption that Mars was lifeless, weighted the interpretation toward the mundane explanation. But here's what we didn't know in 1976. Mars had liquid water, subsurface ice, ancient riverbeds, hydrothermal vents, evidence that accumulated over decades. If life existed on Mars, it wouldn't be sprawled across the surface. It would be sheltered underground where radiation couldn't reach it, exactly where Viking's arm couldn't dig. The soil sample Viking analyzed came from the surface. If Martian microbes existed, they were likely meters below, dormant, or thriving in liquid water. Viking's arm sampled the top few centimeters, a dead zone, baked by radiation. We were looking for a signal in the one place life probably wasn't sending one. There's another detail that troubles astrobiologists, the heat sterilization test. Before analyzing samples, some were heated to kill any organisms. The heated samples produced no radioactive gas. The unheated ones did. That's the opposite of what chemistry predicts. Heat shouldn't silence a purely chemical reaction, it should accelerate it. That fingerprint, the silence after heating, looked biological. It looked like heating killed something, but the scientific consensus had already decided. 1 anomaly could be noise, 2 could be coincidence, 3 that was just bad luck. The case was closed before the evidence was fully examined. In 2019, a NASA researcher named Joseph Seff ran a computer model of the labeled release experiment using known Martian conditions. He simulated perchlorate salts, compounds found in Martian soil that can mimic biological signatures. The result? The simulation matched the data perfectly. A chemical explanation existed. But here's the catch: Seff's model required specific concentrations of perchlorates. We didn't measure those concentrations in Viking's samples. The simulation worked in theory. On Mars, the actual chemistry might have been messier. The real answer? Still uncertain. The data still sat there unresolved. What makes this story haunting is timing. We had one chance to sample Mars in 1976, 2 landers, 1 set of answers, and in that narrow window we may have seen a signal we couldn't interpret, not because the instruments were wrong, but because we didn't understand Mars well enough to trust what they were telling us. The irony is sharp. Modern Mars rovers like Curiosity and Perseverance have far better instruments, but they're not designed to detect life directly. They look for biosignatures, the chemical traces life leaves behind. They're searching for ghosts of organisms, not living ones. If microbial life exists on Mars today, hidden in subsurface water, we might walk past it without recognizing it. Scientists have spent 50 years debating what Viking found. Some argue the evidence points to life. Others say chemistry is cleaner. The truth? We may never know for certain. That ambiguity, that unresolved question hanging over decades, is exactly why the Viking experiments still matter. They asked the right question, they just couldn't fully answer it. So did we find life on Mars in 1976 and miss it? The data suggests maybe. The chemistry suggests no, and that's the uncomfortable truth. We had one shot and the answer was written in a language we didn't yet speak. Today, with decades of Mars knowledge accumulated, we read those old signals differently, but we still can't say for certain what they meant. The Viking landers sent back thousands of images, millions of data points, and one question that science still hasn't fully answered. And that's exactly why we keep looking. Subscribe, because every month there's a discovery that rewrites what we thought we knew about space and about ourselves. Subscribe, because every month there's a discovery that rewrites what we thought we knew about space and about ourselves.